Okay, so hello and welcome again. Today we are going to have this video session for our solutions on a previous seat work we had. Say we have here a beam that is loaded with a pointed load 6 kilonewton at B, and at the same time we have here a couple at D 20 kilonewton meter. So as usual, we are going to have the reactions first and then proceed to the methods introduced, that is by equation method and by graphical method. So we will compare again the two methods in coming up with the shear and moment diagrams. So we take moments at D in order to solve for RE. We have 20 minus 6 times moment arm 4. Of course, we wanted to place there your assumed reaction, so that RE would have a clockwise rotation, so that is plus RE times moment arm of 6. So all of this will be equal to 0. So that RE is equal to 0.67 as computed. So the other reaction, of course, we take moments at E. We have 6 times 2 plus decouple clockwise minus RD counterclockwise multiplied by 6, and that is equal to 0. So that RD is equal to 5.33. So as our check mechanism, we'll take equilibrium equation along the vertical is equal to 0. Okay, so we add the two upward forces, RA and RD. We deduct here the downward 6. So this is equal to 0. So it is really equal to 0. So we are ensured of our reaction. So we're going to place it here. So we're going to do it by method of equation first. So we set x first within the boundaries of AB, and then of course we section it considering the left portion because we are doing it from left to right. So if this is the beam, there will be this portion to be cut, and there is shear and moment along this cut section. Of course, this distance is x, and Vx is simply summation forces y, positive going up and negative going downwards. So here we have a constant Vx is equal to 0.67, and for summation moments AB, so we'll just have to use this as our point of reference. We will have here a sign convention that if we have a concave downwards fiber, that is negative, and a concave upwards fiber, that is a positive. So we have m from A to B is equal to 0.67 times x. So next is to transfer the extent of x up to the boundaries from B to D. Why not B to C? Because BC and BD has no loading. It can cover the same loading at the left portion. So meaning the span BC and CD has no loading. Therefore, the implication is we can have a common equation to that boundary. So this x is extended up to B, C, and D. So this is BCD. So we draw the figure. So we draw the forces on the left portion together with its distance, so that if this is x, this is of course x less 2. So of course we do the same. We take forces vertical for Vx. See the same criteria here, and then all we have to do is to sum up forces vertical. That is a positive upwards direction, and then we less this. downward direction. So we have 5.33 for that. So we also write the moment. We have to use this reference to take moments at this section. So first we have an upward fiber that is 0.67x. We less this 6 causing a concave downward fiber multiplied by the moment arm. So we have now this equation 0.67x minus 6 quantity x minus 2 for our moment at BCD. So we also consider an equation where 20 kilonewton meter will be included. So we can say here that this equation is for just left side of D. So if we wanted to include 20 here, we copy the same equation and consider the 20 just right of D. So this equation is an equation for just right of D. So basically, we have already completed our equation. So of course, you know what to do here. Just designate x values for your coordinates. Of course, we note some equation. AB is applicable only within the boundaries of this span. And then BCD will have this general equation that we have a constant 5.33 along that line. And the moment will be derived from these two equations, just left of D and just right of D for span BCD. And we also have this equation for span AB. Okay, so we are now going to graph this. We can do it by this equation, and we can do it by a direct graphical method. So we will do it by direct graphical method. Okay, so we're going to have these zero lines for the shear and moment. So at A, we have an upward 0.67. So this one. And then from A to B has no loading, so it remains to be 0.67. So that is just left of B. The value is 0.67. So we can verify that in our equation actually. So we have a constant value for AB with the shear of 0.67. And then just right of B, we can apply this equation in which at this point from 0.67 it will go down by 6 units. So 0.67 minus 6, that is negative 5.33. Actually, this is our equation, negative 5.33. Okay. So all throughout, we have no loading, so it will remain to be 5.33. And then it will return to 0 because of this vertically upwards reaction at D. So here it is. So this is the shear diagram. So that is shaded. So remember that the ordinate of the moment diagram will be derived out of the area of this. So we have two rectangular areas, a positive area here and a negative area there. So the first area is 0.67 times 2. So along this point we have no area yet. So up to this point where we have the value. That is a positive 1.34. And we connect that by straight line. Now we less this rectangular portion at the negative zone, and this area here is calculated to be negative 21.32. So we have positive 1.34 less negative 21.32, and that will be approximately equal to negative 20, and that will be connected by a straight line, and eventually it will go back to 0 because just right of D we have here the positive rotation 20 kilonewton meter. Okay, so that tends to close this moment diagram, and this completes the problem. Okay, so let's move on to another problem. Okay, so we have here a symmetrically loaded problem. So if this is symmetrically loaded, therefore the reactions at B and C will just have an equal value, that is the half of all your loadings. Okay, of course we wanted to resolve this 150 pounds per feet into its resultant that is located at the mid of the dimension, and that is 150 times 6, that is equal to 900, and this 900 will combine to the two downward forces both sides, 250 and 250, so that is 500 plus 900, we have 1400, and 1400, the overall total of your downward forces will just be shared by the two reactions. So there you have a 700 reaction for each of these support. So again, by equation method, we are going to do it from left to right. Okay, so we have a set of x here. First, x is within the boundaries of AB, starting from E. So we have here AB. We have here 250, the shear and moment. And this is x. We write VAB, and that is simply equal to negative 250. And MAB, so we take this reference line, that is a negative going downward fiber. So negative 250x. Then we transfer this x within the boundaries of BC. So we just have to transfer that one along this boundary BC. Then we have the illustration. Of course, we have here 250, the 700 here, and the sliced distributed load here. This is 150 pounds per feet, so we wanted to resolve its resultant. We have here the resultant equivalent to 150 times this distance. And what is that distance? So if this is x and this is 4, therefore the other dimension is x minus 4. So that this is 150 times x minus 4. So we always note the internal forces here on the cut section. So we write the equation. So writing the equation, we have our VBC. First we have negative 250 minus this downward 150 times x minus 4, and then there will be no other shear here. We then proceed to the moment along BC. We have this one, negative 250x. We pin this and then apply this, that is downward fiber, so that this is negative. And then here we have another force. So this force will surely have its moment arm from this point, and the moment arm is the half of x minus 4. So x minus 4 divided by 2. So if we simplify this equation, we have this simplified equation. So we now proceed to the next span, which is CD. We'll just have to extend this x up to the boundaries of CD. And then, of course, just the same, we are going to illustrate this one. The cut section of x, considering the left portion. We have the pointed loads. and then the distributed load here, the reaction, and this is 900, and of course along this cut section we have the shear and moment. Okay, so we write the shear at CD, and all of which does not involve the X, and that is our X. So we have positive all throughout within the boundaries of CD. So for the moment CD, we pin this reference point. So 250 here will tend to bend your fiber concaving downwards, and then an upward bending, we have 700 times the distance from point B up to this point. So of course we need to determine this excess distance here. So if this is X and this is 10, therefore the excess here is X minus 10. So we also note the distance from B to C, which is 6. So therefore the distance of this 700 of B from this point of reference is, we have 6 plus X minus 10. And then we have the 900 here will yield a negative fiber. Say we have here the 900, and then the distance from this up to this point, of course this is the half of 6, so we have to write that 3, and then add this plus X minus 10, and then the 700 here times the distance X minus 10. So we simplify this, and this will be our moment equation within the boundaries of CD. So you cover an X from 0 up to X less than 14. Okay, so we can extend this equation just right of D. Okay, so where we involve here 250. Okay, so we copy that and then deduct this 250, and of course it will close to 0. Okay, so this will be our equation. Of course you know what to do. Just delegate again values for X if you intend to determine it per segment. Okay, so we will again do it by a graphical method using the point loads and the area of the uniformly distributed load. Okay, so we draw the line. So this is for our shear diagram. So this starts to 0 line, and then we go down from the left portion. We have negative 250, no loading, so it remains to be negative 250, and then an upward 700 here. We have a positive 450, and then we deduct this area here, and that area is 150 by 6, that is 900. 450 minus 900, that will yield to negative 450 at this line. So we have that to be negative 450, and then we add here 700 units going upwards. It will yield to positive 250. No load, it will remain to be 250, and the concentrated load here will yield to 0. So this is the shear diagram. Okay, we take note of this intersection of 0 and the curve of the shear diagram. Anyway, it is just a symmetrical figure, so therefore this distance of this one is simply bisecting the middle, or we have the half of 6, that is 3. So we also establish the moment diagram out of this by area. Of course, if you desire to have a faster solution, let us compute first for the area of these shapes. So number 1, we have 250 here, and 4, if we multiply that, we have negative 1000. So that is a negative area here. And then another triangle, 450 by 3, that is 750, divided by 2, we have 675. So 450 times 3 divided by 2, or 1/2 base times height. So we have a similar area here, and this is also similar to that one. Okay, so let us have now the moment diagram. We have here the moment M. This is 0. So first we have here 1000, and the connector is, looking at your shear diagram, this is a flat, so therefore this is a straight line. And then we add this triangle here from 1000. 1000 plus 675, we have 1675. And we again less this 675 here, it will go back to 1000 here, and then eventually it will go back to 0 by having this. Anyway, I think we have interchange. We should start with a negative area here, so we reset that one. Starting at this point, we have a negative value, so negative 1000, straight line connector, and then negative 1000 plus 675, we have here negative 325, and it will return to negative 1000 if we are going to deduct this negative triangle here. Okay, so this is where this 1000 area here will yield back to 0. Okay, so what about the connector? 1000, 325, and 1000 here. So this is a decreasing. So when we have a decreasing line, we have a direct logic decreasing concave downwards. And that will be our connector there. And this will be our moment diagram for this problem. Okay, so let us now proceed to another problem. Say we have here a trapezoidal loading. Actually, you have two options here. You divide this by composite areas, by a rectangle and a triangle, or by two triangles. So I'll just divide this by two triangles. So we have this bisecting line dividing this into two triangles, so that we have here the two resultant of the triangle, smaller triangle here at the bottom, and the resultant of this. So all of which are referred to its height measured 1/3 of the base. So all in all, we have a base of 9. Therefore 1/3 of 9 is, we have 3 here and another 3 here for the bigger triangle. So let us have to resolve this concentrated load located at the centroid of this triangle. So first, for the smaller triangle, we have 1/2 base times height, or that is 9 by 0.5, and that is equal to 2.25. So similarly, we have here 1/2 base times height. This is equal to 6.75. So we take moments at support 8 to solve for RC. We have a clockwise 2.25 times 3 plus 6.75 times the excess of 3 from 9 is, of course, that is 6. Then we place here RC. Of course, horizontal at A is 0, so that we have a counterclockwise rotation for RC. So we denote that by negative times its moment arm 9, and that will be equal to 0. So that RC is equal to 5.25 kilonewton. So for the other reaction, we have summation moments as C is equal to 0. We have here a counterclockwise times its moment arm. Another counterclockwise times its moment arm, 6 plus 9 RA is equal to 0. So RA is equal to 3.75 kilonewton. So by checking, we take equilibrium equation along the vertical axis. So we add the upward forces and we less the downward forces. So is it equal to 0? So really it is equal to 0. So therefore we are assured of our reaction. We are now ready to have your shear and moment diagram. Okay, so working with this beam now, we are going now to place our reaction. Say this is 3.75 and that is 5.25. So we will have a section from A to B or B to C. But if we notice, we have a common section for AB and BC because we have trapezoidal loading. So do not ever consider another section for AB and for BC. So it will have a common section here. So we'll just have to place X anywhere within these boundaries. Again, AB and BC will have a common section. Actually, we have the same slice of a trapezoid. Here it is, a downward trapezoidal loading. So we wanted to include this, the reaction at E, and then this is the X distance. We have a horizontal bisecting line here in order to separate two composite areas, the rectangle and the triangle here. This dimension is 0.5 and the other one is a variable. We wanted to express that in terms of y here, so that the height of this triangle is y minus 0.5. Then we resolve for this rectangular portion here, that is base times height, x times 0.5 is 0.5x. We do the same for the rectangle or the triangle here, that having a base of 0.5 and the height of y minus 0.5. So we write that as 1/2 base, which is x, times the height y minus 5.5. Of course, we wanted to have a single variable here, all in terms of x, so therefore y here could be expressed in terms of x by, of course, ratio and proportion. By using the unsliced triangle here, and the height of that whole triangle is equal to 1, we can now say that by ratio and proportion we have base to base, x is to 9, is equal to height y minus 0.5 is to 1. So we cross multiply and then solve for y. Of course, we distribute 9 here. 9y minus 9 times 0.5, that is half, 4.5. Solving for y, we need to transpose this. Becomes x plus 4.5 is equal to 9y. So finally, we divide both sides by 9, so we come up with the value of y is equal to x plus 4.5 divided by 9. So we now write Vx, an upwards 3.75 here, minus this one, downwards 0.5x, minus this triangle, 1/2 x times y minus 0.5. We expand and replace y here, this one, and then just copy that 0.5 there. So we simplify further. We use 9 as the LCD of this inside quantity here. So 9 divided by 9 is 1 times this first term. So we just copy that one. And then 0.5 all over 1 here. So 9 divided by 1 is 9 times negative 0.5, that is minus 4.5. So we cancel that out. We copy those terms. we combine two x's and then divided by 9 times 2. That is equal to 18. So we have here the equation 3.75 minus 0.5 x minus x squared all over 18 for our shear equation. We proceed to the moment. We have mx. So we use this point of reference. So 3.75 is a positive concave upwards. We multiply it by the moment arm x. Then we have this one, the rectangular force, that is negative 0.5x times the moment arm half of x, that is also 0.5 of x. So this is just squared, and then minus the triangular loading here. This is 1 half x times y minus 0.5. So I think this is the expression or the simplified version. And we have to multiply this by its moment arm, that is 1/3 of x. Okay, so expanding it further or simplifying it further, we have to combine the terms of the third term, that is x cubed all over 18 times 3, that is equal to 54. So we have here the equation for the shear and the moment. So this will now be the equation to be used in determining what are the values of the shear at any point in the beam by just designating an x. So in the problem, it requires the shear at x is equal to 3 meters, or what is the shear at point B. So let us just substitute when x is equal to 3. We substitute in the equation. The result is shear at B, and the answer is 1.75. Okay, so the same question is when x is equal to 3, what is the moment at B? Okay, so what will be the moment? So just substitute 3 here. When x is equal to 3, that is actually MB equal to 85 kilonewton meter. So those were the answers in your problem. Now, establishing our illustration here or the diagram, you can always use this one. And then doing it by graphical method, we have for the shear, let us consider this 0 line here. From A, we have an upward 3.75. And then consider all of this area, this is a trapezoidal area, and we know that this trapezoidal area has the rectangle and the triangular result of this figure. So when we add that, we have 9. Okay, because for the rectangle here a while ago, we have a resultant of 4.5 here and another 4.5 for that triangle. So all in all, we have 9. Okay, so therefore these are negative ordinates or negative area of the trapezoid, which is 4.5 plus 4.5, negative 9. So we deduct 9 units, 3.75 minus 9. We have negative 5.25 here, and eventually it will yield to 0 because of this upward reaction at C. Say that is 5.25, and then we connect this by a curve. So looking at this load diagram, your loading here is increasing. So between the load and the shear diagram, we have an indirect logic. If this is increasing, therefore the opposite of increasing is concave downwards, so instead of concaving upwards. So we connect these two lines by concaving upward or downward second degree curve. So here it is. Notice that we have crossed the zero line here, so we are concerned with this point now. So maybe we can delegate that as x. Okay, we can delegate that as x. By graphical method, it is so difficult to do this by graphical method because we have a bisected parabola here. Perhaps you might think that you can use here by ratio and proportion of the parabola, like thinking of this whole parabola with base and height, and you can ratio and proportion a certain point here. But the thing here is that your bisecting line horizontally also bisects this parabola, wherein the ratio and proportion could no longer be feasible. Okay, say this is your bisecting line. This parabola here is not similar anymore to the whole parabola here. So that is the difficulty in dealing with this parabola by graphical method. So this is where the importance of an equation comes in. Why? Because we know that x here is set to locate our shear, which is equal to 0. So this is the condition where we can find x through the equation. So what is the equation? This one. Vx is equal to 3.75 minus 0.5x minus x squared all over 18. So we're going to work with that. Okay, so we'll just have to refer to this. So we set that to 0 because Vx at that point is equal to 0. And then just copy the equation. As we notice, we have the value of x here. X will have a 2 root because this is a quadratic equation. So the first root is actually negative 13.86. So this is impractical to consider as our root. Then we will consider the second root, which is 4.87 meters. So practically, it will still be feasible in our beam, which has a whole length of 9 meters. So x here is 4.87. Okay, so this 4.87 will now be our basis in determining the maximum moment here. Just refer to this location. So here it is. Just substitute 4.87 in this mx equation. So we just say that when x is equal to 4.87, our mx is equal to 10.194 kilonewton meter. So we place it here. Okay, at this point we do not have any area yet, so it will start with the 0 and there will be no couple on your load diagram. And then if you might wonder what will be the final value here. So what we do is just to substitute x is equal to 9 and it should be equal to 0, okay, because moment diagram always yields to 0 or closest to 0. So when x is equal to 9, your moment will yield to 0, so we have a 0 here. So connecting these three, we have here a decreasing curve here. So between this, we have a direct logic wherein if we have a decreasing, we have a concave downward connector. And here it is, we have the highest point to be equal to 10.194, and somewhere in 3 meters, we have a value of 8.5 kilonewton meter. So this is measured 3 meters from A. So this is the shear and moment diagram. Of course, we need to indicate also the degree of the curve. So of course, the first degree is the loading. So just add 1 there. Therefore, this is second degree curve or parabolic curve, and this one is a third degree curve. So this is the shear and moment diagram closest to 0. So we have noticed that sometimes you need to supplement your graphical method by equation method, okay? So that is the importance of having mastery on both methods, because both will supplement, or the other one could be your check mechanism in order to ensure the correctness of your solution. So we will proceed to another problem on the next session. So thank you for listening. I think you have to practice a lot.